Hello everyone. So in this pre-lecture tutorial we're going to sort of close this loop related to our discussion of chemical structure and function by discussing intermolecular forces. And basically intermolecular forces refer to attractive interactions between molecules. Okay, and those come in several varieties. Now we have what we call dispersion forces. Sometimes they're referred to as London dispersion forces. We have dipole-dipole interactions, and we also have hydrogen bonding. Now if you notice, I sort of have a line here separating hydrogen bonding from ionic bonding, because technically ionic bonding isn't a true intermolecular force, simply because we're not dealing with molecules anymore when we're dealing with ionic compounds. Ionic bonding represents a force that applies to the attraction between ions. But I did include it in this discussion because in addition to understanding how each of these intermolecular forces occur and how they work, we also should have a thorough idea of how the strengths of these forces relate to one another. And so for that purpose, I've included ionic bonding in the discussion. So let's go ahead and summarize what each of these types of intermolecular forces are, and then we'll go through an example exercise so that you can see how these concepts are applied. And so we'll begin the discussion by discussing London dispersion forces. And in order to understand London dispersion forces, we have to understand how it's possible for molecules to induce dipoles. And this word induce means that we're forcing these dipoles to happen. And really the reason that these dipoles can be induced is that, if you recall, atoms have this electron cloud around them, okay? And we know that from earlier in the year. And the electrons within the electron cloud are in constant motion, scattering about, okay? And when this happens, if it just so happens that at any one moment in time, the electrons are roughly evenly distributed around the nucleus, then basically the electrons shield the nucleus. And so if I have another atom of neon, let's say in this example, and again these electrons are also moving around randomly as well, then basically what's going to happen is each of these neon atoms have their nuclei pretty well shielded, and so as a result there is no net positive negative interaction that might occur between these two neon atoms, and they won't necessarily be attracted to each other. And so you're not going to get any particular force pulling these atoms together. However, since these electrons are constantly moving around, something like this might happen, where all of the electrons in any one moment of time happen to migrate to the same side of the atom. So in this neon atom, it's sort of towards the bottom left. And what that does is it concentrates the negative charge within the neon atom to the left-hand side, the bottom left-hand side of this atom, momentarily. Again, this doesn't last very long, but in any one particular snapshot, if we could take a snapshot of the electrons zooming around within the electron cloud, this may happen. Okay, and what that does is, in addition to the negative charge being concentrated in the lower left, what it does is it leaves the upper right portion open and the nucleus exposed. And so that means that just for a split second, this neon atom on the left-hand side of this figure happens to have a temporary or induced dipole. Now, what that does is it will affect any other neon atom that's nearby. Because of this partial positive charge, because of this induced dipole, if there's a neon atom nearby, then these electrons will want to zoom over towards this towards this temporary induced positive charge, having the same effect on this neon atom on the right-hand side of the figure. Now, this atom also happens to have all of its negative charge concentrated primarily in the lower left-hand portion of its volume, whereas in the upper right-hand portion of its volume, basically the nucleus is exposed and there is a temporary positive charge, inducing a dipole. Because we have this positive to negative interaction, then for a split second, these two neon atoms are attracted to one another. Right? But what will happen is, just as easily as these electrons happen to be in this state, since the electrons are in constant motion, they'll start moving around again and they'll move over so that it looks more like this again, and then that temporary attraction is gone, or it's vanished. And so, as a result, basically, London dispersion forces are temporary. They're temporary attractive forces. Also because they depend on these induced dipoles. These induced dipoles aren't very strong, and so it's considered a rather weak attractive force. And since basically the motion of the electrons within the electron cloud is common to all atoms, then basically London dispersion forces occur in all atoms and molecules. And so basically all compounds experience these London dispersion forces. However, for non-polar compounds, London dispersion forces are the only intermolecular force that acts upon the compound. Okay, now let's compare that to dipole-dipole interactions. Now, if I have a dipole-dipole interaction, that means an interaction between two dipoles. And if you recall from earlier in the chapter, basically dipoles that are not induced, basically this refers to permanent dipoles, and we find permanent dipoles in polar compounds, polar covalent compounds. Basically what happens in dipole-dipole interactions is that, as we remember from the previous section, in a polar compound, I have one part of the molecule that has a slight partial negative charge and another that has a slight partial positive charge because of differences in electronegativity. And so because of this permanent dipole, if I have another molecule of that same compound and the dipole works just the same in this second molecule of hydrogen chloride as it does in the first, basically there is a slight partial positive charge around the hydrogen and a slight partial negative charge around the chlorine. Again, because of electrostatic interactions, this partial positive charge and this partial negative charge will actually attract one another and cause these two molecules of hydrogen chloride to be attracted to one another. Okay, and this attraction is always present. It's not an induced or a temporary dipole like in London dispersion forces. As a result, this interaction is actually stronger than the interaction of London dispersion forces. But again, these types of interactions are present in polar compounds. So polar compounds actually have two types of intermolecular forces acting within them. They have London dispersion forces, and they also have dipole-dipole interactions. Though the stronger of the two forces that's responsible for the attraction between these polar molecules would actually be the dipole-dipole interactions. Now, as it turns out, there's also sort of a subset of dipole-dipole interactions that's actually even stronger still. I have what's called hydrogen bonding. And hydrogen bonding represents a dipole-dipole interaction between compounds containing the following bonds: hydrogen-fluorine bonds, hydrogen-oxygen bonds, or hydrogen-nitrogen bonds. Okay, the reason for that is that the difference in electronegativity between the two atoms within these bonds is actually very large. And so that magnifies that dipole-dipole interaction that we spoke about in the previous slide. And so it still works on the same premise. Basically, say here in the water molecule, I have an oxygen-hydrogen bond. And so I have hydrogen bonding present in water. The hydrogen would actually have a slight partial positive charge, and the oxygen would have a slight partial negative charge, because the oxygen is much more electronegative than the hydrogen. This partial positive charge will interact with the partial negative charge of an oxygen in a second water molecule, causing an attraction between these two water molecules. In class, we had a brief discussion yesterday about how water is a liquid because of this strong intermolecular force, because of this strong interaction. And so when we consider those compounds that have each of these types of bonds, then basically now we have a total of 3 potential interactions. We have London dispersion forces, we have dipole-dipole interactions, and we have hydrogen bonding. But because of the large electronegativity difference that takes place in hydrogen bonding, then basically hydrogen bonding is actually stronger as an intermolecular force than dipole-dipole interactions, and obviously much stronger than London dispersion forces. Okay? Now, we also have ionic bonding. Now again, as I mentioned before, this is sort of for reference. Here, if you notice, I have a lithium cation. Notice that this is a full positive charge. It's not a partial positive charge anymore. Like in the water molecule, the hydrogens have a partial positive charge. Here, the lithium cation has a full positive charge, a full transfer of an electron away from the lithium to cause a full positive charge. Here, this fluoride ion has a full negative charge. And so as a result, this actually leads to a much stronger interaction between the anion and the cation. And so a much stronger attraction. Than hydrogen bonding, and a much stronger attraction than dipole-dipole interactions, and certainly much stronger than London dispersion forces. And so typically ionic compounds tend to have the strongest attractions between species. As compared to covalent compounds that may experience hydrogen bonding, or dipole-dipole interactions, or London dispersion forces. And so let's actually take a look at a selection of compounds, and let's see if we can pick out what type of intermolecular force might be the strongest intermolecular force for that particular compound, and let's actually rank their relative strengths compared to each other. And so here I have hydrogen bromide. Okay, there's only one bond in this compound. And so as a result, I need to understand what type of bond this is. I need to know whether the bond is nonpolar covalent, polar covalent, or if it might be an ionic bond. And so if you recall, the way to do that is to consult my electronegativity tables. And so here's hydrogen's electronegativity at 2.1, and here's the electronegativity for bromine at 2.8. And so that would be electronegativity of 2.1, electronegativity of 2.8. The difference in electronegativity is 0.7. And if you recall, for me to have a polar covalent bond, then I have to be between 0.5 and 1.8 in that difference in electronegativity. And so basically, hydrogen bromide is a polar compound because it only contains one bond, and that bond happens to be a polar bond. Then I have oxygen. So here's the Lewis structure for oxygen. There's only one bond, the double bond between the two oxygens, but since these atoms are identical, then the difference in electronegativity here is 0. So this is a non-polar bond and also a non-polar compound. If I think of this compound, that's methanol, then basically if I draw the Lewis structure for methanol, then I have the following as the Lewis structure for methanol. Now, if you recall from our work yesterday, basically the carbon-hydrogen bond is nonpolar. The electronegativity difference is only 0.4 between carbon and hydrogen, and so we're outside of this 0.5 to 1.8 range, and so each of these carbon-hydrogen bonds are nonpolar. But the carbon-oxygen bond is polar, and so is the hydrogen bond, and the bond dipoles would point toward the oxygen. Since we have bent molecular geometry around this oxygen, that means that I'm going to have a concentration of a partial negative charge around this oxygen and a partial positive charge around the carbon and the hydrogen that's bonded to this oxygen. So that means I do have a molecular dipole. So this compound is polar. But not only is this compound polar, but there's an oxygen-hydrogen bond. And if you recall, if I have an oxygen-hydrogen bond, then that means this molecule experiences hydrogen bonding. So putting this back into our chart, the intermolecular force that I can expect for hydrogen bromide, since that's a polar compound and there is a bond dipole, should be dipole-dipole interactions. Oxygen, though, is nonpolar. And so as a result, the strongest and only intermolecular force that I can expect between oxygen molecules should be London dispersion forces. And then lastly, for methanol, because of the oxygen-hydrogen bond and the fact that there's a molecular dipole, that means I can expect a strong interaction to be present because of hydrogen bonding. Now, if you recall the relative strengths, hydrogen bonding of these three intermolecular forces is the strongest. So I'm going to rank that as number 1. Dipole-dipole interactions are the next strongest, so I'm going to rank that at number 2. And London dispersion forces are our weakest intermolecular force. So I'm going to rank that as number 3. Okay, so go ahead and work on the follow-up assignment, trying to apply these concepts. We're going to go ahead and discuss this concept further in class tomorrow, and you'll also have an application activity to do to help reinforce this skill. If you have any questions, by all means email or bring up your questions in class.